weeks, and it's great that you're coming out, and I'm very happy to see you braving the drizzle that's out there. I'm from Ireland, and that sort of drizzly weather is sort of what I'm used to, so it doesn't bother me too much. So as I was preparing this lecture, what I kind of wanted to talk about is what I'm going to talk about in the second half of the lecture, which is really the pulsar stuff. And I kind of wanted to talk more in detail about the pulsar side of it. But then I kind of realized, well, you have to sort of know the...
You want to cut the lights on the screen?
Yeah. Are people happy in their seats now? So I can put the lights down.
Up a little more.
The never-ending feud.
A little more.
Oh,
Okay. That's tolerable.
That's tolerable. All right. Okay. So one of the things I want to sort of implant in your minds before we get into the lecture is that when you think about those of you who were there last week, the sort of situation I described about pulsars and magnetospheres and electron-positron pairs and non-thermal radiation and all the sort of mess that is going on inside a pulsar, while that's pretty complicated stuff, for most of you, or for many of you, I would say that's the first time you ever saw that. So I wasn't really trying to challenge another idea. Like there wasn't an existing notion of how pulsars work, and now I'm bringing in all the blobs and the, whizzing around that sort of disrupts your pre-existing idea. Whereas what Einstein did is exactly that. He tackled what people had believed and understood and felt comfortable with. And they had to introduce a new idea, a new way of thinking about that same stuff. And this new idea kind of generated a lot of weird things, weird stuff that maybe up until that point we wouldn't have been comfortable with. And so while describing something complicated, perhaps complicated is difficult, describing something complicated that replaces an existing idea that you're comfortable with is even more difficult. So the first half of the lecture, I'm going to quickly try to go through what it is that Einstein was thinking about and the sort of ideas he had and how these sort of ideas he had translates into the weird phenomenon. And I want you to kind of bear with me that, while everybody kind of doesn't want to believe that this weird stuff happens, it really does happen. All right. Now with that little prelude, let's see what I have teed up. Okay. Yeah. So to remind everybody where we are in the series, and for those of you who are showing up for the first time, all the awesome stuff you missed. We talked about, basically setting the stage. We talked about how neutron stars come to be. Last week we talked about how it is that the emission comes out. And today is the first week where I'm going to talk about the tool of the pulsar. Never mind that it's a big blob. Let's just think about it as a big clock. Okay. So, all right, here we go. So Einstein, I guess, wasn't the best student, it seems, by some people's assessment. And a lot of the time, he seemed like the inattentive sort of weirdo in the back who wasn't really doing his homework and wasn't really paying attention. And the reason for that is because he spent all of his time, or a lot of his time, just kind of thinking of things in his mind. And he picked two kind of basic principles to start it all off. And basically, everything that I'm about to show you throughout the course of the couple of first few slides kind of is a direct repercussion of these two sentences, like two sentences, and then then Einstein's weird stuff happens. So the first thing is that there's no preferred reference frame, which means that if you perform an experiment in one place, and people are observing it from another place, the laws of physics should be the same. The laws of physics shouldn't appear different depending on where you are looking at them. And I should remind everybody that the laws of physics as we know them have been measured on a spinning ball in space, which is the Earth. Everything we learned about physics, we learned pretty much in laboratories on the Earth, and the Earth is hurtling through space around the sun and spinning on its axis. So if somebody kind of watches that from some other frame of reference, a different spinning ball or a spaceship moving in a different direction, or I don't know, some other moving entity that moves relative to that, it shouldn't surprise you that the laws of physics would still pan out the same way. So that was number one. And then number two was that the speed of light is constant. And again, we measure the speed of light. Like if we set up a little tabletop experiment and we bounce a laser beam across, the light that comes out of the laser beam isn't getting any extra speed from the fact that the Earth, as I said, is whisking around the solar system. It just moves at the speed that it moves, independent of the fact that the thing that shoots it out happens to be moving through space or moving relative to some other observer. So the speed of light is constant, and there's no preferred reference frame. If you're comfortable with that, then you've got to swallow everything that comes afterwards. All right, so what comes afterwards? So I tried to draw a bus, but I kind of didn't like the bus. So imagine it's a bus, and we're looking down on the bus. It's a magical bus that's mostly aisle, and everybody it's moving this way, and these are the seats. And for some reason, one of the bus engineers decided to take out one of the seats and put a little mirror in place. So this is our bus. Now, imagine you're on the bus. So you're not moving. As far as you know, you and the bus are moving at the same speed. And you're sitting in the chair. I'm sitting in the chair. One of us is sitting in the chair with a little laser pointer. And we bounce the laser beam across the bus. It bounces off the mirror and bounces back. Now that's exactly what we do when we measure the speed of light, except the bus. If we bounce light between, down the corridor on the physics building and measure it, that physics building is whisking through space, so it might as well be, sitting on a bus. So when we measure the speed of light, and we measure what it is, now imagine a different observer watching this same experiment, except they're not on the bus, they're, hovering over you, well, not hovering over you, they're on the bridge looking down at the bus. What did they see? Okay. They will see me shoot the laser beam. Then the laser beam, because the bus moves and the laser beam goes, in this representation, the laser beam goes across, but the bus is moving, so as far as I'm concerned, sitting on the bridge, the laser beam actually moves this way, bounces off the mirror, and bounces back to me. So that's how an observer who isn't moving with the bus sees this thing pan out. Now, statement number 2 says the speed of light is constant. How can, in the same amount of time, a laser beam travel this distance in one place and travel this distance in another? It seems like, as far as I'm concerned, watching what's happening on the bus, I will tell you, well, light has to travel much faster because it goes a much larger distance compared to these guys. And so Einstein kind of scratched his head for a long time and kind of wondered, what's going on? And he decided he wasn't going to let go of the fact that light travels at the same speed, and so he decided that clocks tick at a different speed. So these people's clocks have to be traveling slower than my clock. That's just the only explanation. If light can travel a less distance from their frame as compared to my frame, but we assume, or we won't let go of the fact that the speed of light has to be constant, then the only place you can hide that problem is, well, the distance changes, so it's not actually their distances are different than they think they are, than I think they are, and that's another way to look at it, or that their clocks travel at a different speed. And so this is what Einstein wrote down in 1905, which is basically the theory of special relativity, and its moving clocks run slow. So that's the deal. If you believe these two things, that's the inevitable. You can't escape that as a conclusion. All right. So that's special relativity. That's 1905. There's no talk about gravity. No, just talk about very fast-moving buses. All right. Most of the time, we're not on incredibly fast-moving buses. We don't encounter this. So, it took a. By the way, I should say that while this might seem weird, this is like totally normal for physicists. So one way that this is sort of instantly verifiable for a physicist is that there are these particles that have short lifetime. So like the muon or the pion, these are particles that like to like abandon their state and move into a different state. And you can measure the lifetime, how long it takes for the pion to exist and then convert it to its new state. And you can measure that if you move the pion really fast around the accelerator or if you move it like slower in the accelerator. And you see that it lives a different amount of time depending on whether it's moving fast or stationary. And so the lifetime of particles is one way we can get access into this exact situation. None of the sort of particle physics that we do with the LHC or the Tevatron or anywhere like that would make sense without the special relativity. So it seems weird, but it's true. So now what about gravity? How are we doing? 10 minutes. So Newton here, and it's just some apple tree picture I grabbed off the web. And so Newton's ideas, they were wonderful ideas and did the job perfectly well for a very long period of time. And his ideas were that space and time are independent quantities. Gravity is an attractive force between two masses, and orbiting bodies obey Kepler's laws. And this allowed them to predict everything that was happening in the solar system to high precision, and they're all very happy with that. Hooray for Newton. However, Einstein, now that he starts thinking about his bouncing laser beams in fast-moving train cars, comes up with a different idea, that space and time are not independent. He called it space-time, or I don't know if he called it space-time, but that's what we call it now, space-time. And massive bodies cause the curvature of space-time, and this curvature affects the trajectory of light and the passage of time. So, what does that mean? So, while I had some other slides I took them out, I had too many, but I want to talk about where gravity goes wrong. And so this was something that was already known in Einstein's time, was that this is a picture of the transit of Mercury across the sun. This is the sun here. This little blob here is Mercury. And people had known even in 1905 that Mercury showed up a little further along in its route around the sun than we expected. And this is a sort of discrepancy in 100 years. So it's 0.012 degrees per century. So already astronomers were good enough in the early 1900s to sort of have picked up on this. And so, they started to feel like, we thought we had this figured out. We thought we had orbiting bodies figured out. Why is Mercury showing up a little bit earlier than it's supposed to? So this was like a nagging problem. And there are other ways to try and explain this, and some of them maybe mitigate the effect. And that's by assuming that the sun is not a perfect sphere, but that it's oblate, has like sort of a badass. And basically that can affect the calculations. And so you can make this effect be slightly less bad if you assume certain things about the shape of the sun. And it's not, maybe the sun is a little bit oblate because it is spinning around, so it could have appeared on a bit of a fat ass. Okay, so what's the solution to the problem? So this is very nice that we're talking about this in 2015, because that's that's the field equations of gravitation by A. Einstein, and it was submitted in November 1915. So we're in the 100th year of general relativity. So it's nice that we kind of talk about this in the 100th year. And yeah, I don't know what that says. But one of the things that comes out of this is that massive bodies bend light. And so maybe you're familiar with the idea of a gravitational lens. So if you are at the Earth, say, and you look through something, maybe the sun, or maybe something more massive like a distant galaxy, and then you look at an object behind the galaxy, it can appear, the real position is here, but it actually appears up here because the light bends, and so it enters in at a different angle. And this is a direct outcome of Einstein's calculations. And while that may seem kind of weird and esoteric, you can just look in space with the right kind of telescope and see it happening. This is a really beautiful example of what's called an Einstein ring, which is basically there's one This is a very massive galaxy, and behind it is another galaxy, but we actually see that other galaxy appear kind of like a ring because it's getting bent around. And this is another example. This is a nice clean system because there's only one nice, almost spherically symmetric gravity source here. In this case, there's a galaxy cluster, so there's a cluster of galaxies, so the lensing source itself isn't as regular. And so we see these sort of arcs rather than nice circles. But it's exactly the same thing. There's a weird shaped gravitational lens in here, and it makes a weird shaped lensing signal. And so yeah, this is true. Gravity bends light. Now, one thing this is cool when I was thinking about this week. So everybody is kind of familiar with this idea that, you know, if you drop a ball and you drop like a coin and they're different materials or whatever, that they arrive at the Earth at the same time, you know, like people dropping stuff off the Leaning Tower of Pisa and all the rest of that. Why does that happen? We don't really know why that, I mean, nobody really knew why that happened. Wasn't really like the underlying idea of why that happens. Never really, it was just sort of an empirical fact. An empirical fact, this happens. So look, here's a nice picture, or a little clip from the BBC to demonstrate it. So this is a bowling ball and a feather, and they're dropping in a large vacuum chamber. So air resistance is taken out of the picture. And this video has been slowed down, so if it appears to fall slower than you expect, it's because they slowed down the video. So take it away, BBC 2. They have music. I haven't got to plug in what the music is. Inspirational music. Hooray! Now, why does that happen? Einstein came up with a way of looking at this problem that I'm going to show you now. I hope this all makes sense. Here we go. So, what do you imagine was someone falling off a house, actually, off the roof of their house? And if they're falling off the roof of the house, and as they fall, like their keys or something falls out of their pocket. And so then, and the person who falls off the house and his keys are falling at the same time. And so as far as he's concerned, him and the keys are just in the same frame. They're not moving relatively to each other. So he kind of thought, oh, that's kind of cool. You wouldn't know that you were, if you couldn't see anything around you, if you couldn't see the ground hurtling towards you, you would just see the keys and you'd be like floating. You would feel like you're floating. And you know, now we all see people in the International Space Station, you know, with blobs of water and drinking them and all the rest of that. And so this idea that if you fall into a gravitational field with everything around you, and then you put that everything around you in a box, and it feels like you're floating. So when you're in free fall, you don't kind of feel the gravitational field because you're obeying what it tells you to do, and so you don't feel it. And so this is supposed to be a man in a box falling, and the fact that these two circles have different colors is supposed to sort of convey to you that, you know, this one's made of lead and this one's made of styrofoam or whatever. So there he is. Now he thought about this situation. He said, okay, well, we just saw the feather and the bowling ball fall. So when the man is on Earth and he's sitting in his box and he drops his things, they fall at the same speed like we just saw. Now imagine we take our spaceman, and instead of having him float around, we strap a rocket to his box, and we send him up at exactly the speed that things accelerate on the ground. So he is now moving up with an acceleration that is the same as the acceleration that these would move down on the Earth. So now, in his box, as far as he can tell, he drops his feather and his bowling ball, and they fall to the ground. So his experience is exactly the same as his experience. And we call what's happening here what Newton would have called as the force of gravity pulling it down. And so you can imagine, well, if we're accelerating up with some force, then this situation is equivalent. There's an equivalency there. So whatever physics happens in this world should happen in this world. So now you imagine, all right, what's the next slide? Great. So now Einstein was thinking about our man getting pushed up by a rocket and experiencing gravity as if it was gravity, the same as this man. Now we thought if there was another guy out here shooting a laser beam across the box. So, you know, as I'm out there in space waiting for the box with the man to go by, and I guess imagine there's a window in the box, and I shoot the laser beam across. What would that laser beam look like to him? Look like that. That's how as the beam moves across and he moves up, as far as he's concerned, the beam would appear to bend over. So yeah, you have to have asymmetric windows. You can't have the windows on the same place. You have to have one up and one down in order for it to pass through. So yeah, in this little box, as far as he knows, he doesn't know he's moving through space. He just feels like he's sitting on some gravity source. You know, outside observers will say, oh, you have a rocket strapped to you, and the real reference frame is the Earth, and all the rest of that. But you can't do that. It all has to work. The laws of physics have to work independent of the reference frame. And so Einstein concluded, well, if this is what would happen to a light ray in this moving box, and as far as this guy knows, he's just experiencing the force of some gravity source underneath, then this is what has to be happening to us on the Earth when there's a gravity source. And that's why light is bent by, well, not necessarily that's why it is, but that's a way to think about why it is that light is bent by gravitational masses, by massive bodies. Stunned silence. Is everyone on board? We good? All right, I'll take a quick question.
Well, this also means gravity is a fictitious force, according to Einstein, right?
Well, I don't worry about the categorization of it that way. What works for me is the tools, and you can, call it fictitious. You can look at it in different ways. I don't consider it helpful to call it that. Maybe Einstein did, but I don't want to get into that. All right, massive bodies cause light to bend. Anything I have with red and yellow is like the take-home point. Those of you who have been coming, you maybe have figured that out, but pretty much anything else can be ignored except the big red and yellow thing. And so yeah, this is a nice picture. This is what Einstein was doing in the back of the class, scratching his head. And then in 1915, he wrote the field equations of gravity. And we don't need to worry about that because we could just, boom, there it's happening. I should point out that there's some news coverage at the moment because the Hubble Space Telescope is 25 years old right now. And so these are awesome images from Hubble. And yeah, go Hubble. Now, what's coming up next? All right. So if that was weird, that the gravity bends light. What else? This is another weird one. All right. So, I shouldn't have showed you the picture. Let's just think about what a clock is. What is a clock? So when you think about a pendulum is like something that swings over. A clock is typically something that repeats, has a periodicity. That's pretty, you get your little hourglass, and it takes a certain amount of time, and then you turn it over again. And so it's something that repeats over and over again. So let's imagine now we have, dug some physicists out of the basement, and we said, make us a clock that shoots out a laser beam pulse every interval, like every second or every nanosecond, it shoots out a pulse. So now we have awesome laser beam clock. All right? And so we asked the physicists to build us 2 laser beam clocks, so every time the thing ticks, it shoots out a laser beam. And now we set one of these clocks up in our, what seems to be a gravitational field as far as the man inside is concerned, but let's think about it in the other way, that it actually has some engine powering its motion. But the person in here doesn't know that. And he has two of these awesome laser beam clocks, and he sets one on the floor and one on the ceiling, and he shoots one up and one down. Now, because this whole system is moving, if you're up here, you're moving away from the laser. If you're up here, you're moving away from the laser beam that gets shot out. So, beam comes out, and you're moving away from it. So it arrives later, a little bit later. However, if you're sitting down here and you're looking at this laser beam coming down, you're moving toward it, and so it arrives a little bit earlier. So if you're looking up this clock, and you don't know you're moving, you don't, as far as you know, you're just sitting on some solid ground that makes apples fall. If you're sitting there and you're looking up at this thing, you see this thing coming at you faster. Just the light beats, the light pulses just arrive at you faster than you would measure by looking at the clock beside you. So, what this means is that the gravitational fields affect, or massive bodies, I prefer to think of them, massive bodies affect how fast clocks tick. Clocks that are closer to the massive body will tick slower than those further away from it. Now, this is all very weird and everything. Feels very weird, but basically the starting point that the laws of physics have to be the same, independent of reference frame, and that the speed of light moves at a constant speed c. If you swallow those two initial conditions, then you end up with this weird scenario that clocks tick at different speeds relative to each other if they're in different parts of a gravitational field. So, big red clocks. The clocks closer to a massive body run slower with respect to the one further away. Now, can we leave it till later? Yeah. So, this one is a bit maybe harder to visualize because I don't have an awesome image of a slow-moving clock from the Hubble Space Telescope. We do later with the pulsars, this has been experimentally verified in an experiment that was done, I think in '70. Well, it was done before that, but then it was done better in like the mid-'70s. And so, Carl Alley at University of Maryland, he got like one of these very fabulous atomic clocks that tick very awesomely, very well. He actually got 6 of them, and he put 3 of them in a plane, and he put 3 of them on the ground. And so the clocks that are up in the airplane are further away from the gravitational field of the Earth, and so the clocks up here should tick faster than the clocks down here. So that's the big red box, and that's our little diagram. And so here's Mr. Alley there. This is one of his awesome clocks, what the atomic clock looked like in the '70s. This is the plane that he flew the other clock in, and he basically flew around the Chesapeake Bay for 15 hours in this military plane. And this is the time difference between the two clocks. So it's there. This is before the flight, during the flight, and after the flight. So you see, they measure the same speed, and now he takes off, and they start to drift. And then when he comes back down again, they move at the same rate there. So this is an awesome plot, I think, because it has a couple of effects that I'm going to point out. The first is that this big military plane, you can't just like fly up 35,000 feet. It needs to go up there in stages because it's carrying a lot of fuel. It just needs the fuel to burn in order to be a lighter plane. And so what you can see is that for the first 5 hours, he flew at 25,000 feet. So how much the clocks diverged progressed in this way at a constant rate of divergence. After 5 hours of burning the fuel, he was able to go up to 30,000 feet. And so you can see this section of the journey, these 5 hours, it increases at a slightly higher rate. And finally, after 10 hours of burning 10 hours of fuel, he can get up to 35,000 feet. And so we can actually see him get further away from the Earth, and the clock ticks faster and faster as he gets further away. And so after 15 hours, flying around the Chesapeake Bay. What they measured was 47.1 nanoseconds difference. Now, Einstein would tell you that it should be 52.8 nanoseconds. That should be the difference you expect when you're in a different part of the gravitational field, when you're further away from the massive body. However, don't forget our moving clocks run slow. This plane flying around is moving at a speed relative to the clock on the ground, and so this is it running slow. So it runs 52 seconds faster because it's higher up, and then it runs 5.7 seconds slower because it's moving around, and the cumulative effect is at 47.1 nanoseconds. This is like brilliant. Einstein is right again. Hooray. Okay, yeah, so that's why I said those things. Wonderful. So yeah, this is the special relativity effect, and this is the general relativity effect. And they did a lot of stuff I didn't describe. Like they were bouncing laser beams off the plane to measure exactly where it was and how far away and how fast it was moving in order to like really do a great job of it. So yeah, and a cool experiment. And so yeah, this is, I was just Googling around and I found this headline. It's from 2005, or I think. So yeah, somebody else must have done a better job, but I like this. Time moves faster upstairs, confirming Einstein's relativity. And then down here in the text, they tell you that those people who are keeping you awake by banging on the floor upstairs are actually, you know, going to die sooner than you will, because they are living in a place where the clocks tick faster. So. All right. So this is all weird. It seems all weird the first time you see it, especially if you're used to not thinking about it this way. But this is 100 years since these ideas were put out there by Einstein, and they've pretty much been verified 100%. And if any of you are out there, driving back to Michigan or whatever, and you use one of these guys, your GPS systems wouldn't work the way they do. That's precisely if they do, they would drift. You would be in the wrong place. You'd never make it to the lecture on time. If Einstein wasn't right, and we didn't put these effects into our clocks that are on the GPS satellites and so on. All right, 11:32. No, that's not bad. So, what about pulsars? What do pulsars have to add to this stuff? So last week we heard, and those of you who were brave enough to come, heard all about the complicated physics of emission from pulsars. Just today we're going to forget that, and we're just going to have clocks in space! All right. The best kind of clocks you could want, big, fat, heavy ones. Now, I kind of introduced this idea on the very first lecture. The very first lecture, I showed you this picture, and I said, if we have a clock, if we have a pulsar that's moving around, then we can see this effect. We can see it when the pulsars arrive a little bit earlier than we would normally predict, and a little bit later than we normally predict. And that's how we can measure the binary parameters, by kind of seeing these curves and then modeling these curves, and then we know how it is that the two bodies orbit each other. So, the very first binary pulsar, that's a pulsar in a binary system, that was ever discovered, his name is 1913+16. It was the first one ever discovered. It has a period of 59 milliseconds, and the binary orbit is 7.75 hours. So this is something that's heavier than the sun, spinning, 16 times a second, and also moving around something like super fast, like the other body it's moving around is a neutron star as well, and it's quite possibly another pulsar, but the beam isn't pointed at the Earth. But we can measure the mass of the companion, and the mass of the companion comes out about 1.4 solar masses, and so it's most likely a neutron star, 2 neutron stars. And for 30 years, it was the most relativistic binary known and the best laboratory for studies of general relativity. And Joe Taylor and his grad student, Alan Hulse, won the Nobel Prize in Physics in 1993. And as I was kind of putting this slide together, I thought to myself, there was another Nobel Prize for pulsars that was won by Anthony Hewish. So I should say that Joe Taylor was like a professor in Boston, and Russell Holtz was his graduate student. So it was a graduate student professor team that found this guy. And it was a graduate student professor team that found the first pulsar, Anthony Hewish and Joshua Bell. But Joshua Bell didn't get the Nobel Prize, whereas Russell Holtz did get one. So I don't know what that's saying, I just thought it was interesting. Well, yeah, well, that's... So yeah, I thought I would just whip up a bit of controversy there again. All right, so the telescope that they used to discover this is called the Arecibo telescope in Puerto Rico. Those of you who were enthralled by the 1995 thriller GoldenEye would have seen a scene where they're sliding down this into some master villain's lair or something like that. From all these pictures that you see of the Arecibo Observatory, it looks actually like a big bowl, like an actual kind of surface. But this is the view from underneath. And so it's actually like a giant meshy grid. And so all the rain that falls in Puerto Rico can just slosh through the grid, and you don't have to support all that and make all this green stuff grow. So you can see it's supported by, there's like these three huge antennas. And then they support this gantry walkway up here. And up there, then there's a receiver. And this receiver can move along kind of along this sort of curve here. And so that's how you point. Sort of light that was coming in over here will bounce and kind of ride over here. And so if you want to look over in that direction, you put your receiver over here, and vice versa. So the dish isn't steerable, but the antenna is a bit steerable, and so you're able to steer this telescope. And this is the largest radio telescope that we have. And so yeah, in the early 70s, Joe Taylor and Russell Holtz found this binary pulsar. And so this is one of the figures. I don't know if this figure is in the handout. Oh, I should say, by the way, before we move on, that today's handout, for those of you who have it, I didn't have time to write like a little narrative of my own, so I just stole a bunch of text from a Scientific American article. And so some of that text might seem a bit disjointed because it was pulled out. But one of the figures, I don't know if I gave you this figure, but so this is a figure, so this is the binary orbit time. This is the time it takes for the pulsar to orbit its neighbor. And what you can see on this axis here is what he calls the pulse repetition frequency. And so this is the Doppler effect as the pulsar moves closer towards us and moves far away from us, we see the frequency shift. So for fun, I thought I would try and demonstrate that. For those of you, I mean, everybody's heard it because they hear an ambulance go by and that kind of thing. So I have a, hope I don't take anyone's eye out now, no lawsuits. So I have a tuning fork. Makes a nice tone, and now today, before you guys came in, I sellotaped a piece of string to it. So let's see how this would sound if it was moving around in a binary orbit. This would be a circular orbit, so we expect it to sort of come in and out very evenly. This is a binary orbit, and so it actually won't. That's why it has this sort of weird shape, because it's in a binary orbit rather than a sinusoid. The people in the back here, no? A little bit anticlimactic, but there you go. I saw somebody do this, but they had a huge tuning fork. I don't want one of those.
What do you hear down there?
I hear kind of some beats. I hear beats, actually.
No, you don't hear any variation because you are at the same distance.
Oh yeah, but no. I don't hear this.
Or something.
Well, I mean, I wasn't quite at the same distance. It's not like I had it like directly between my two ears. So let's have a look at this figure again. So yeah, we basically, with this pulsar, we can see the Doppler effect, and this is exactly how we're able to measure the binary parameter so well. Another way you can plot this is to look at the radial velocity. So you can look at it as to how does the frequency change, or how does the radial velocity change. And so what we can see is that this when it's coming right towards us, it's moving before it turns around. It's moving at 300 kilometers a second. And so just for a sense of scale, the Earth, as it moves around, is moving at 30 kilometers a second. And a bit closer in, Mercury is moving at 47 times a second. So this is moving sort of relativistically almost. It's not quite. It's 0.1% the speed of light. So it's very, very fast. Another thing you can do is you can look at, so rather than looking at the frequency, how does the frequency kind of come in and out, you can look at the actual arrival times of the pulses, like when do the pulses arrive as the thing moves around. And so as the thing goes from being as far away from us to as close as it gets, the pulses are arriving 3.6 seconds difference. And so that's how we can measure the sort of projected distance of this orbit. And so it orbits at about 1 million kilometers diameter. So the diameter of the orbit is about 1 million kilometers. So you can just tell that just by reading this number and putting in the speed of light. And this is known to an accuracy of 1 part. And at the time when this paper was written, which was in the 80s, this size was known to 1 part in 150,000. So this is an incredibly precise knowledge of how this thing is moving around. All right.
And now it's more precise?
We have more data and better telescopes, so yeah, it's more precise. So this is just a picture. So we have our pulsar that's going around, our other neutron star that we can't see as a pulsations from it, so it's essentially just a massive body that we don't see. The point of closest approach is 1.1 solar radii. Remember that this thing is heavier than the sun, 40% heavier than the sun. His buddy is 40% heavier than the sun, but the two of them approach each other. That's not me, is it? The two of them approach each other with only the radius of the sun, our sun, the Earth, the sun in the orbit. And there's a figure in the handout that I gave you, and the figure in the diameter is wrong. The sun is only half the size it should be. So I didn't make that figure. I stole it, and then after I stole it, I realized that they made a mistake. What they call the diameter of the sun, and that is actually the radius. And so just to kind of give you a sense of scale of how tight this binary is, remember now, this isn't two planets. This is two things heavier than the sun orbiting each other and they get as close as the radius of our sun. So the largest separation distance is 5 solar radiuses. And just to put this in context, the Earth is 215 solar radiuses away from the sun, and Mercury is 66 solar radiuses away. So this is like right on top of it. And so one thing you can tell just by looking at this diagram is that the pulsar is moving in and out and in and out of the gravitational field of its companion. So the experiment we had about the plane, flying up above us and then coming down and the clock being different, you can imagine this as a clock being really far away and then going in for a little bit and then being really far away again. And so we should see the effect of the pulsar now as a clock itself. If you think of it as a clock, we're putting a clock into the gravitational field and then a little bit out again and back in again. Can we see that? So just to kind of fill you in with some stats, the binary pulsar is, that's his name. It's a very stable clock, ticking 16.94 times a second. There's way more digits here, I didn't put them in. It weighs 1.4398 solar masses with this error. This is how well we can measure the mass. It orbits a companion with 1.3886 solar masses. It orbits 7.75 hours. It moves at 0.1 the speed of light, and it moves in and out at these solar radii. And so Einstein in 1915, when he came up with this theory, he didn't think such a laboratory like this would ever exist. And so if he knew about this, I would imagine he would have a pretty happy face. All right. So that situation, we can measure that. So this is called a relativistic time delay, and it's about an amplitude of 0.04 seconds, 4 milliseconds. So we can measure a 4. So remember, in the case of Carol, we had 40 nanoseconds. Now we're like 4 milliseconds. So it's a huge effect, and we see this drifting in and out as the pulsar moves in and out. And so there are the two effects. Remember, there's the fact that the moving clocks run slow, so because it's moving, it runs a little bit slower, but because it spends some time in a place where the gravity field is higher, then then it slows as well. Yeah, so sometimes it spends time away and then it takes a bit faster. Yeah. So yeah, you combine those two effects, and this is what is measured, and it's measured incredibly accurately, as perfect measurement.
What is it? I'm not clear on what it is that's moving faster and slower. Is it the velocity as it orbits, or is it something to do with the light?
The clock is moving slower. The orbit, the rotational speed is moving slower and faster. All right. So another effect. So this is called the Shapiro delay, and I didn't set this one up. Earlier, but I hope I can explain it. So remember, we had a clock sitting up here in the plane, and we moved it in and out, or the pulsar moving in and out. Now imagine this. So the situation we have with the Holtz-Taylor. So this is how a binary might look. We have something orbiting something else, and depending on the inclination. Depending on how the orbit is tilted on the sky, if it's completely face on, that's how we would see it. And if it's completely edge on, we would well, that's not completely edge on, but almost edge on, it would look like that. And so sometimes, if this was a situation, the radiation from the pulse radiation coming from the pulsar would come out towards us, and it wouldn't have to traverse much of the gravitational field because it's in front of it, but then when it goes behind it, the light ray itself has to go through the gravitational field. So in the first case, it was the clock that was moving through the gravitational field. Now it's if you're shooting the light through the gravitational field, and as the light moves in a place where clocks run at different speeds, they get delayed. And so this is called the Shapiro delay. This is measured for a different pulsar, not the binary pulsar, but a different binary pulsar. The effect is much more noticeable on this one because the binary orbit is much more edge on. But we can see during the orbit of this pulsar from 0 to 1 full orbit, we see 17 microsecond delay. So, as it almost is eclipsed, the light ray has to come through the magnetic field, through the gravitational field, and so it gets delayed, and then it comes to the other side, and the delay recedes again. And so with this kind of measurement, you can measure the precise curvature of the field. You're sort of sending a beacon probe kind of behind it and probing different parts of the field, and so you can measure the precise curvature. So this doesn't have any form. Einstein wrote down exactly what shape it should have, and this is the predicted shape. The black line is what Einstein said it should be, and the data points is what we measure. So it's phenomenally accurate.
So
I gotta wrap up. I'm almost there, and then we can go to town on the questions. All right. Now, the business with Mercury. So Mercury was seen to be, the orbit of Mercury was seen to be doing this. So that is the point of closest approach seemed to be moving around. And it was seen to be 0.01. So the angle that this changes, this angle was found to be 0.012 degrees per century. With the binary pulsar, it's moving 4.2 degrees per year.
Wow.
This is a huge effect. Now, I watched a lecture. I'm gonna try and explain something that is kind of cool. I watched a lecture on YouTube given by Joe Taylor, the guy who discovered this, and he gave a nice kind of idea of why this happens. And so, imagine I am like a massive body making a big gravitational field, and there's some bodies out there orbiting. Now it takes time. It takes time for the body out there to feel the field. The field moves out from me kind of at the speed of light. So if you can imagine the field coming out from me, constantly informing everyone, I'm a massive body, I'm a massive body, I'm a massive body, I'm a massive body. Okay? And so they're all going, oh, there's a massive body, so I have to do this. So they're constantly being told by the massive body where it is and how to behave and how to move in response to that. But that information takes time. So the massive body is here. He says, I'm a massive body, I'm a massive body. And that takes time. And so by the time the orbiting companion hears the message, I'm a massive body, the orbiting companion has moved to a different place. So he's like, the massive body is over there. But he's moved a bit. And so he's actually being told to move to a place where the massive body isn't, because he has moved in the time that it took for the gravitational kind of information to be moved across to him. He has moved in relative to that. And so he sees the place that he should be orbiting moving around. From his point of view, it's moving around because it takes a certain amount of time for it to be received by him. And so that's why it processes.
Wow, it's the best explanation.
Well, it might be your best explanation. Anyway, that's how Joe Taylor helps us understand that. And so, so we can see, now remember the other plots I showed you, what was on the axis was hours. So they could see the Shapiro delay happening throughout one orbit. Like throughout one orbit they could see the Shapiro delay, or throughout one orbit they would see the relativistic clock delay. However, this is plotted over years, from 1974 to 1982. So in order to perceive this change, although it's a huge change, 2 seconds, but still, in order to measure this precession as well as they have measured it, it took them 10 years to make this curve. And so the line up here is what Newton said should happen. The black line is what Einstein said should happen. And that's the measurement. And so what's plotted here, rather than plotting the kind of change of the angle, they just plot like how much earlier the photon is arriving than you would expect, because it's even closer. And so this is how the picture looked in '82, and now this is how it looks. So this is now from 1975 to 2005. So that diagram I showed you is up in this little pink box up here. And this is a prediction of gravity. So by now, after timing it for 30 years, it's off by 45 seconds. So it's a huge triumph. So, with the idea that I said about the kind of news to travel, for the time for the news to travel to the orbiting companion, for him to be told, hey, there's a massive body, you better, behave. For him to be told that another thing is happening. And this is the big prediction of Einstein, and that's what's confirmed by this plot. Like, when he comes up with his curve, the explanation for this curve is that it's emitting gravitational waves. So, as they orbit each other, they're losing. So the energy of the binary system, is being sapped away. That's what the orbit is not only processing, but it's also decreasing. Yeah. So this is a hugely exaggerated figure. But as the thing processes, it also spirals in, and so the energy of the binary is getting sapped away, and it's being lost to gravitational waves. So this source is radiating gravitational waves, a prediction of Einstein, and that prediction of Einstein is confirmed by this shape. And so, so this is how this is a better figure, better than the one in the handout. So this is how the binary shape will look over 250 million years. So if we're around in 250 million years time, this is how tight the binary will be. And the gravitational waves will be lost. So sort of ripples in space-time coming out of the binary.
Does the orbit become bigger?
No, your orbit shrinks.
But you showed that it was bigger in 250 million years.
No.
In the previous...
No, that isn't... That's not what I intended to show. I intended to show how it looks now, and then how it will look in 250 million years. And so this is what's happening. This thing is radiating gravitational waves. Now, gravitational, and we might talk about this more in a couple of lectures time about like what it is, the gravitational waves, and how they behave. But they behave a little bit differently than ordinary waves on the sea or whatever. They have a particular, it's a quadrupole wave. That's just, never mind that, but it's a special way. And so, if you didn't have a quadrupole wave, you would get that curve wrong. The curve that was there. And so that tells you that it's a quadrupole wave, and that's exactly what Einstein predicted. Now, that's just words, and we might go into that in more detail in another lecture. But the take-home message is that, yeah, Einstein predicted the loss of gravitational waves, which would have predicted that curve, and that's exactly what we measured. So I just wanted to put I just wanted to put this in to kind of give you a feeling for how precise we know stuff. Like, you don't really need to look at the numbers so much as to look at how many digits there are and how small. So this is how fast the period is. The frequency, 16.94, blah, 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 blah. So on the first day, if those of you who were there on the first day, I tried to say, what's kind of crappy about astrophysics sometimes is because we don't control it. It just does what it wants. It's not a laboratory science. We can't, change stuff and configure it to our likings. So it's hard to do high precision science in astrophysics. And that's why pulsars are so great, because they allow you to do ultra high precision stuff. So because I spent so much time talking about Einstein and preparing the kind of Einstein side of it, I didn't get to talk so much about the binary pulsar. The double pulsar. So this is a system that was discovered in 2003. And this is an amazing system because now we see the pulse from two objects. So rather than us seeing the pulsation from one of the objects, we see the pulsation from both of them. The period of one of them is 23 milliseconds. The period of the other is 2.8 seconds. The masses are known, 1.37, 1.25. And they orbit each other at 2.4 hours. So the whole stellar binary, the original binary pulsar system was essentially 8 hours of size. This is only 2.5. So this has evolved and spiraled in closer. And luckily for us, the beam of the second, the companion object, is also visible. So all the tests that you did with the first guy, how big is the orbit, what's the Shapiro delay, what's all the tests you can do it twice. You just ignore one and measure it all from the second one, and then ignore that one and measure it all from the first one, and they get perfect consistency. So this is that same gravitational wave loss figure. You can see how well it's sampled. It's measured with incredible accuracy. This is being timed by the Arecibo Observatory in Australia. It's a southern hemisphere source, and this is just the Shapiro delay. That delay when one pulsar is sort of almost eclipsed by the other one, and you see delay of 100 microseconds, which is amazing. Now I'm finished, but I wanted to give a plug to people. So there's something called Einstein at Home. And this is a project where you can kind of download software on your computer, and then when your computer isn't being used, it gets used for scientific computing. And so one of the things the Einstein at home people do is they look for pulsars. So data from the Parkes telescope or data from some other radio telescope. It takes an awful long time to sift through all that data and find the pulses and find the pulsars. And so it takes enormous computing resources. And so this is a way that they can sort of ask the community at large to provide their computing resources. So it's like a screensaver. When your computer isn't doing anything and the screensaver comes up behind the scenes, it's actually punching the numbers. And what's cool about the Einstein at home pulsars is that if your computer finds one of the pulsars, and your name gets in the paper, in the journal article that announces a discovery. So so with that, I'll leave you with where we're going, and thank you very much. I'm going to take questions, but I want you to take it easy on me because I'm not a general relativistic expert. I do my best, but I don't have all the answers. So now there was people who wanted to ask me a question during the lecture. Who are they? And have they given up? Oh, you're the man. Are you satisfied? No, I'm not satisfied now. All right, well let's.
All right, just a little bit. Are you talking about the massive body communicating in presence to the orbiting body?
Yeah.
How is that communicated?
Yeah, I don't want to say.
Okay.
So in QED, in the situation where you have an electron and a positron. So if you think about the orbiting of two massive bodies, if you just imagine that system as being an electron and a positron, or an electron and a proton. The same idea can be invoked there, but this information is sent by the photon. So photons send this information. And so while I kind of use that as a description, while Joe Taylor kind of used that to kind of describe what happens, there is a theory of a graviton, and this is like a gravity information unit. And some people who are trying to merge quantum mechanics and general relativity, there are people who are trying to put these two separate theories and sort of make a meta-together theory. And so they use something called a graviton, but I absolutely don't talk about that because I have no opinion. But I don't necessarily, I just think that's a way to kind of think about it. It's not, doesn't have to be like absolutely scientifically correct in detail, it's just a way to think about what's going on.
What if a supernova popped off, on the way home today? Would it be of interest to people who are studying neutron stars?
Yeah.
I mean, is it a matter of, I don't get the time frame for these. Is it going to be generations before that?
So there's two things. So the question is, are we interested in seeing these supernovas happen? And yeah, we are. And 2 weeks ago, when we talked about supernova and the formation of neutron stars, I pointed out one that happened in 1987 that happened in the Large Magellanic Cloud. So that was nearby, because the Large Magellanic Cloud is near to the Earth, or near to the Milky Way. It's not in the Milky Way. The last good guy to happen in the Milky Way happened about 300 years ago. Kepler saw it. And so we're talking that time scale for them to happen near enough. I mean, they're happening in other galaxies that are more distant from us all the time. So, they're being, hundreds are found per year, but they're so far away that you can't really get into the problem in the same way you can if they're in our own galaxy or in the Magellanic Clouds. So yeah, we'd be very interested in them, and yeah, you gotta wait a couple hundred years for a good one.
But I mean, after one pops off, how long would it take to become a neutron star?
So the neutron star happens kind of at the same time as the explosion. The neutron star gets born, and the kind of shockwave gets sent out from that. This I covered in a good amount of detail 2 weeks ago. So my slides from that are on the web, and you can go through those slides and hopefully get a better feel for that. But yeah, I covered that in great detail 2 weeks ago. All right. Go ahead.
Now you said that the light going through the gravitational field is affected. How is the light going through the gravitational field affected besides changing direction?
Well, it's the Shapiro delay, which is that if you imagine a light, you imagine the light being like a driver, you know, like imagine the light ray, like a photon, is actually a dude in a car, and he's looking at his speedometer, and he's like, gotta keep me at that exact speed, you know. He's going to stick at exactly the right speed. Now we have this into close to the massive body. What happens is time ticks slower in that place. And so in order to keep at the same speed, in order to have that thing saying kilometers per hour or whatever it is, because the hour term, what measures an hour, time, that changes. And so the speed stays the same if you measure it with that time, but the speed, if you measure it without time, the speed looks like it's different, and that's why it's a delay. So it appears to us as a delay, but it appears to the driver of the car as everything's fine. But what's happening in his world is that his clocks are ticking at a different speed. And so that's how you resolve the idea that the speed of light has to stay at the same speed. It stays at the same speed, but the clocks that are kind of measuring it or ticking at different
So it
speeds.
went slower or faster? The speed?
It will go slower.
If the time goes slower,
The clocks tick slower.
and so the speed is slower. Yeah, otherwise we get speed all the time.
I'm only going to do this for about 15 minutes because I didn't get out of here for an hour last week.
I just wanted to know the relationship between the pulsars you're talking about and the Cepheid variable stars.
So what's the relationship?
Yeah, the ones of pulsars are related to the absolute brightness, and you haven't covered that. I'm just wondering what the relationships might be, because I know they're important tools in astronomy.
Yeah, so that anything that's periodic can sort of be tapped into as a tool. Like that's kind of like a metronome of any kind. So the Cepheids are sort of a star that has like an expansion and a contraction. And so they are very useful, but they're like not nearly as precise and awesome as pulsars. But they're still, in the world of astrophysics, it's very hard to find anything that's like the same every day. And so they're still very useful, but they don't have the kind of precision.
But the brightness is related to the pulsing.
Yeah, the luminosity is dependent on how wide you are when you oscillate in and out. This is a particular kind of star that kind of has sound waves and compression waves that flows out and come back in again. But this happens over weeks rather than over fractions of a second.
So the orbit getting smaller in 250 million years, shrinking on that binary system. You offered an explanation in terms of emitting gravitational waves.
Yep.
It seems like something is going away or given off. That means something should be decreasing, and I'm not clear what that is. If it's energy or even mass. Or
Energy.
both.
The same thing.
Energy.
The energy is decreasing, yeah.
So, but E equals mc squared, so are they losing mass through the emission of gravitational waves?
No, they're losing their binary potential like that. They're orbiting each other, and that has a certain energy, and that's what's being lost.
Is there any way that the mass energy equivalence fits into that I haven't?
I mean, that always is happening, but I mean, like E is equals mc squared. That's true, but that is not that equivalence is not needed to explain the gravitation.
It's just they're getting closer.
It's just they're getting closer. They're not.
Things get closer, lose potential energy.
Yeah.
Okay.
You seem reluctant to say that time slows down. You keep rephrasing it to the clock slows down. So which is it? But it's not.
Well, that's a difficult question. I'm glad you picked up on my care with the phrasing of it, because time as something that we experience, as an experience of ours, not as the oscillations of some atom in a atomic clock. Time as we would experience it is kept exactly the same. If we are in a, right now we are in a, the clock's tick at a different speed for us than it does for the astronauts in the space station. Like if they put an atomic, I'm sure they have loads of atomic clocks up there, they're ticking at a different rate. But the astronauts up there see time passing. Well, it's only a tiny, tiny effect. But if you did an Einsteinian kind of thought experiment and thought about it, the person who experiences the clock ticking slower experiences it ticking exactly as they would expect it to. So they don't feel a passage of time difference. The only way you can see this is a relative way. That's why it's called relativity. Clock A relative to clock B ticks differently. But if you are in the world of clock A or if you are in the world of clock B, it all happens the same to you.
I want to make sure I heard your explanation correctly before when you were talking about the Shapiro Delay. You showed a curve.
Yeah.
And it looked very much like a gravity well. Did you say it has the same geometry or no?
Oh, it is a gravity. It is what you would think of as a gravity well. Yeah.
Right, thank you.
Is the delay, is that what's causing the orbit to lose the energy? Because it's the loss of the energy is what's causing the gravitational wave, right?
Yeah. No, I mean, all of this stuff is intertwined, but I don't think it's the delay. It's not the delay.
What's causing the orbit to lose energy?
The radiation of gravitational waves.
But why is it even radiating a gravitational wave?
Because that's how, I mean, the field equations of Einstein tell, so the way Einstein said it, I hope I can quote correctly, mass tells space-time how to curve, and space-time tells mass how to move. And so the moving of mass through space-time causes the space-time to wave out.
Like the video.
All right, I gotta go 3 more minutes, so those who are dying to go on, Roy.
Yeah, the image of the bus that you had at first with the mirror, suppose you have 2 buses, and they're passing in opposite directions. Each one will say, your clock is going slower than mine. How can that be?
So, what you gotta look at it from so the second bus, okay, you said there's 2 buses. Well, the way I set it up, there's already a second bus. It's the Earth whisking through. You can only position, you can't position the third person. A third person looking at 2 buses would see exactly this thing and would all make sense to them. When you are in bus 1 and looking at bus 2 go the other way, you have to consider yourself as you and bus 1 are staying together. Nothing is moving. Everything is moving relative to me. And so the concept of both things moving only happens from the third observer. A third observer who sees them both moving, and they would see the situation happen in one and happen in the other, and it would look like that. The second bus guy, he's the same as from his point of view, there's no third observer. He's observing what's happening in the bus that passes him. The fact that he is moving relative to some other guy that's watching it from the sidelines, that doesn't factor in. So it's only the relative velocity.
Well, just figure each bus as feeling that it's standing still, okay? So bus B sees bus A going by and says, your clock is slower than mine. A is saying the same thing. A says, I'm standing still and you're moving, and your clock is going slower than mine. So how can they both be going slower than each other?
They are. I mean, they only are going slower to each other relative to some other person. You're trying to.
Well, no, it's relative to each other. I mean.
Well, if you see a bus go by, the situation you're describing is the situation I'm describing. It doesn't have to be a second bus. It can just be someone watching the first bus. If someone in that bus sees me set up a weird situation, it's hard to do with that way. So I don't know if I can untangle that for you. You're gonna have to think about it. It is consistent. Maybe I'm failing in my task. All right, I got one more question. It is totally consistent. I can't, but I can't do it right here any more than that. All right, last person.
Mine's simple.
All right. Those are the hard ones.
With the airplane deal, they were measuring gravity, right? And then in astrophysics, you measure gravity. I was wondering about the instrumentation. I've always been puzzled how they measure gravity. What kind of
So we don't really measure gravity. I mean, we're trying to measure the effects of gravity. But and what's going to happen in the last lecture, I should tell you this very last lecture, I can come, I have prior publication. So a colleague of mine who is working on a gravitational wave detector on Earth called LIGO will hopefully do a better job of explaining it. But we don't like have a gravity meter like we go, ooh, there's some gravity over there. Well, gravity does stuff, and we see that stuff happening with the Hubble telescope or with a pulsar or whatever, and then we infer the behavior of gravity from that. Okay.
With the airplane, they were measuring gravity.
Well, they were measuring. What they were measuring was how the clock ticks.
Right.
Okay. That's what they're like. They had one clock and another clock, and if Newton's laws were the same, you put one clock upstairs and you leave one downstairs, and then you bring them down together, and they should register at the same time. And they show. So it was a clock comparison experiment. So they were just measuring how the clocks, what was reading on the clocks, and the divergence of those two numbers was exactly what would be predicted by Einstein.
I see.